Remember Miller's planet from Interstellar? That endless water world orbiting dangerously close to a black hole, where an hour on the surface meant years passing elsewhere. The wild part? The science behind that time dilation is real. But even more exciting, that kind of mysterious planet might not be science fiction at all. Just 48 light years away, which is not that far in the scale of universe, there is GJ1214b, a cloudy enigmatic world that scientists believe could be a giant water-covered planet with thick vapor skies and deep alien oceans.
We've been looking up at the stars for millennia, wondering if we're alone in the universe. The first exoplanets weren't discovered until 1992, orbiting an unlikely host, a pulsar. In 1995, we found the first planet around a Sun-like star. Since then, we've identified thousands of these distant worlds, each one stranger, more fascinating, and more extreme than the last.
And yet, in many ways, we've just scratched the surface. Hello, my name is Lily, and today we're diving into the worlds beyond our reach to explore all the wildest planets of endless firestorms or vast oceans, skies that rain diamonds, and landscapes lit by two suns. In the search for exoplanets, we aren't just looking for planets. We're searching for answers to some of humanity's most profound questions. How did we get here? Are we alone in the universe? Could life as we know it exist elsewhere?
For most of human history, the word planet meant one of a handful of familiar worlds orbiting our Sun, like Mercury, Venus, Mars, etc. That changed when astronomers confirmed the existence of exoplanets, revealing that planets weren't unique to our solar system.
The term comes from the Greek prefix exo, meaning outside. While these distant worlds are still planets in the traditional sense, celestial bodies orbiting a star, they don't belong to our Sun's family. So it's just a technicality. Instead, they circle other stars, sometimes in environments wildly different from anything we know.
Some exoplanets are gas giants larger than Jupiter, others are rocky like Mars, and some are covered in lava oceans or shrouded in ice, locked in eternal darkness. There's even the possibility of rock planets, wandering through space without a star to call home. The staggering diversity of exoplanets shows that our solar system is just one variation in an endless cosmic experiment.
Before their discovery, exoplanets were a matter of speculation. Now we know that the universe is vast and the number of stars and planets out there is mind-boggling. Our Milky Way galaxy alone contains an estimated 100 billion stars, and most of them have at least one planet orbiting.
This means there could be trillions of exoplanets just in our galaxy, each one offering a new opportunity for discovery. Each new world reshapes our understanding of planetary formation, habitability, and perhaps our place in the universe.
However, exoplanets don't come with labels that tell us what they're made of, whether they have water or if they could potentially host life. We need to gather clues, hints from the way light interacts with them, their size, and even their chemical makeup to get the full picture.
The closest star to our solar system, Proxima Centauri, is 4.24 light-years away. That means when we look at Proxima Centauri, we're actually seeing it as it was over 4 years ago, before it even became the object of our study. And yet within that star system there is an exoplanet, Proxima b, orbiting in its star's habitable zone.
In scientific terms, this means the region where liquid water could exist on the surface if conditions are right. The possibilities are thrilling, even though this exoplanet is so far away it's nearly beyond our reach. Yet Proxima b isn't alone. In fact, it's one of the thousands of exoplanets discovered in the last few decades.
But we can't just look at any planet in the universe and assume it's an exoplanet like Earth. Planets come in all shapes, sizes, and forms. With the rise of powerful space telescopes like NASA's TESS or James Webb, we're beginning to gather data at a rate never seen before. These observatories are designed to peer into the distant cosmos and provide insight into the atmospheric makeup of exoplanets, their temperatures, and even signs of potential habitability. And while these telescopes can't bring us closer to these worlds, they are paving the way for breakthroughs that will get us closer to the dream of one day reaching them.
What makes the search for exoplanets even more exciting is the technology driving it. Instruments that can measure the smallest variation in light as the planet passes in front of its star or detect the faintest of chemical signatures are the cutting edge of astrophysical science. These discoveries aren't just theoretical, they're pushing the technologies we use here on Earth.
One of the most fascinating finds in recent years is Kepler-16b. This planet orbits two stars, just like Tatooine from Star Wars. As it moves around its binary star system, it experiences two sunsets, making the very idea of day and night unlike anything we can imagine here on Earth. But while it's not habitable, its discovery reveals just how diverse and strange the universe truly is.
Every new piece of data about an exoplanet brings us one step closer to answering the biggest question of all. Could life exist on a world that's not Earth?
With thousands of exoplanets lighting up our telescopes, scientists created a way to cut through the cosmic crowd, the Earth Similarity Index. It's a numerical measure that estimates how much a far world resembles Earth.
The ESI isn't a direct habitability score, it doesn't guarantee life, but it provides a quick comparison based on a planet's physical characteristics. Scientists input factors like a planet's size, density, surface temperature, and escape velocity. It's the speed needed to break free from the planet's gravity. These are run through a formula that outputs a number between 0 and 1. Earth naturally scores a perfect 1. A 0.9 means a near twin, a world that looks remarkably familiar. Drop to 0.7 and you're in Mars territory. Interesting, but not exactly screaming welcome home. Let's break it down a bit.
Size and mass are major players in the ESI game. A planet that's too small, say less than half Earth's radius, may struggle to hold onto an atmosphere, leaving it exposed to space. Too large, above about 1.6 times Earth's radius, and it might turn into a mini Neptune with a thick hydrogen-helium envelope, making a solid surface unlikely. The ESI favors rocky planets with radii between 0.8 and 1.2 times Earth's.
Temperature is another make or break factor. The ESI focuses on whether a planet's surface temperature falls within the sweet spot for liquid water, life's favorite ingredient.
This depends on its distance from its star and how much stellar energy it absorbs. Too close and it's a scorching wasteland where water vaporizes. Too far and it's an ice ball where nothing flows. The ESI zeroes in on that perfect middle ground, not too hot, not too cold.
Finally, the atmosphere ties it all together. The ESI doesn't directly measure atmospheric composition. Analyzing exoplanet atmospheres from afar is tricky. But remember the escape velocity factor? Here's where it matters.
Scientists use it along with a planet's density to estimate whether it can hold onto an atmosphere. Too weak a gravitational pull, and gases escape into space. Too strong, and you might end up with a thick, crushing atmosphere like Venus, trapping unbearable heat. A thin one, like Mars's, offers little protection from radiation and temperature swings. The sweet spot? An atmosphere stable enough to support liquid water on a surface.
Despite all these factors, ESI isn't a guarantee of habitability. Mars scores around 0.7 due to its size and density, yet its steam, carbon dioxide, heavy atmosphere, and cold climate make it inhospitable. Venus, despite being similar in size to Earth, scrapes by with an ESI of about 0.44. Its hellish greenhouse effect is making it anything but welcoming.
Some exoplanets like Proxima b and Kepler-442b have ESIs above 0.8, hinting at promising conditions. But we have very little information about their atmospheres. For example, recent analysis of data from the Proxima Centauri system reveals that the star's frequent and intense flares likely strip Proxima B's atmosphere and expose its surface to harsh radiation, making life there highly improbable. For years, scientists have speculated that the ingredients for life, water and carbon, could exist in many forms across the universe. That's why we look for planets in the habitable zone, where temperatures could allow for liquid water to exist, a key ingredient for life as we know it.
But what if life doesn't need water at all? The very concept of habitability is expanding as we find new planets with environments unlike anything we've encountered on Earth. Maybe some kind of different life is thriving there. What makes these discoveries possible is the technologies being used to detect exoplanets. The process is far more advanced than simply pointing a telescope and hoping to spot a planet.
Astronomers use techniques like a transit method, where they observe the slight dimming of a star's light as a planet passes in front of it. There's also the radial velocity method, which detects the wobble of a star caused by a gravitational pull of an orbiting planet. With these techniques, astronomers have uncovered planets both near and far, from the tiny to massive.
But we're not just discovering exoplanets anymore. We're beginning to study them in detail.
For example, the James Webb Space Telescope, launched in late 2021, is a game changer. Its unprecedented resolution allows scientists to analyze the atmospheres of exoplanets, looking for chemical signature like oxygen, methane, and carbon dioxide.
If we detect these gases in the right combination, it would be one of the biggest discoveries of our century, evidence of life beyond Earth. Yet the search isn't just about finding another Earth-like planet. It's also about understanding the diversity of planetary systems in our universe.
Take the TRAPPIST-1 system, for example. It contains 7 Earth-sized planets, 3 of which are located in a habitable zone of their ultra-cool star. These planets vary in composition, size, and atmosphere, and studying them could provide insight into how planets like Earth form and evolve. Observations of exoplanets can answer some questions not only about Earth, but also about the mysteries of the formation of our solar system. For example, gas giants like HD 209458b.
Let's be real, you're probably wondering what's up with these weird namings, right?
So, exoplanets are usually named based on the star they orbit. For example, our hero is named after star 209458 from the Henry Draper catalog. Letter B means that it is the first planet discovered around that star. Similarly, Kepler 22b refers to a planet orbiting Kepler 22, a star catalogued by NASA's Kepler mission, with B indicating it's the first planet found there.
The star itself is technically marked with the letter A, but we usually skip that part in casual conversation. So yes, the systematic names help scientists keep track of exoplanets in the ever-growing field of planetary discovery. Of course, sometimes they also give them nicknames like Hot Jupiter for giant planets close to their stars, or Super Earth for planets larger than Earth but smaller than Neptune. The planet from the beginning of the video, GJ1214b, often called Waterworld, for example.
HD 209458b also has a name, a series. It is notable for being the first exoplanet where the atmosphere was detected through observations, thanks to the Hubble telescope. This exoplanet is a hot Jupiter, a gas giant with an atmosphere so hot it evaporates into space, forming a tail of gas.
Scientists have studied the series to better understand the atmospheres of other gas giants, which in turn teaches us about our own solar system's evolution. It's a reminder that even planets that seem inhospitable can teach us a vital lesson about the universe's workings. But it's not just the planets themselves that are intriguing. It's also what they mean for the future of our space exploration. While we're still far from sending spacecrafts to distant exoplanets, upcoming telescopes will transform how we study them.
NASA's planned Habitable Worlds Observatory, expected to launch in 2040s, aims to directly image Earth-like exoplanets in the habitable zones of some Sun-like stars, searching for signs of life in their atmospheres. As our ability to detect and analyze exoplanets improves, so too will our ambition to one day visit them, not just with telescopes, but with robotic probes or even crewed missions in the distant future. One of the boldest ideas in space exploration comes from Breakthrough Starshot, an ambitious project envisioned by Yuri Milner, Stephen Hawking, and Mark Zuckerberg. Announced in 2016, this initiative aims to send hundreds of small spacecraft, known as starships, on a journey to Proxima Centauri. These postage stamp-sized probes would ride ultra-thin laser-driven sails, reaching speeds of up to 20% the speed of light, a staggering 60,000 kilometers per second. At that velocity, they could reach Proxima Centauri in just over 20 years, meaning a launch in 2036 could see them arriving around 2057.
But the journey is only half the challenge. Once the starships reach their target, they'd beam back images and data. But even at the speed of light, their signals would take over 4 years to reach Earth. That means, if everything goes perfectly, our first interstellar postcard could arrive around 2061. Breakthrough Starshot initiative could make humanity an interstellar species within our lifetime, offering a glimpse of alien worlds we've only imagined.
The search for exoplanets is a reminder of just how small and how vast our place in the universe is. It's a journey that spans the outer reach of our technological capabilities and pushes the boundaries of what we know about life and the cosmos. Every discovery raises new questions.
As we look to the stars, we are not just peering into the unknown, we're beginning to understand it. And with each discovery, we come closer to answering two of humanity's oldest questions. Are we alone in the universe? And why are we here? Thank you for your time. See you in the next video.